In this question, we'll be looking at solving for a delta G value under non-standard conditions for this reaction, which is the decomposition of ammonia into hydrogen gas and nitrogen gas. And when you are asked to calculate delta G under non-standard conditions, you'll be using this formula. Okay? Delta G is equal to delta G naught, that's the standard conditions, plus RT ln Q. Okay? Where Q now is the reaction quotient, which we learned from chapter 13. So that's the first step in solving this problem. Keeping in mind Q, just like K, is products over reactants. We're going to be using partial pressures in this problem. Okay? So my Q value, right, is equal to my pressure of hydrogen cubed, because it has a coefficient of 3, times my pressure of nitrogen, over my pressure of ammonia squared, because it has a coefficient of 2. Looking at the slide, my partial pressure of hydrogen is 0.250 cubed. Right? All of these would have units of atmospheres. My pressure of nitrogen is 0.870. And my partial pressure of ammonia is 12.9. I'm going to plug all of these into the calculator. Okay, so I've got 0.25 cubed with a 0.015625 times 0.87 is going to give me 0.0135 on top. 0.0136 when it's rounded, divided by 12.9 squared on the bottom, which is 166.4. My final value of Q is equal to 8.17 times 10 to the negative fifth. Now I can go back up here. Okay, I'm solving for delta G equal to delta G naught, which is equal to 33.0 kilojoules per mole. That information also comes from the slide and would have to be provided to you. Okay. The R value in these types of problems is 8.314 joules per mole Kelvin, which is a clue there that your T, your temperature, has to be in Kelvin. Yeah, sorry, I came off the slide a little bit there. T has to be, as I mentioned, in Kelvin, so we are at 25 degrees Celsius, something else that the slide would have told you, at 25 C. Right, 25 plus 273 means we're working at 298 Kelvin. And we multiply by the natural log of our Q, 8.17 times 10 to the negative fifth. So I'm going to do some simplifying. First, natural log of 8.17 times 10 to the negative fifth. That's equal to negative 9.41. I've got my 298 Kelvin still, 8.314 joule per mole Kelvin, plus my unchanged delta G value. Multiplying these three together gives you negative 233.03881. Okay, but it's a negative, so plus a negative, I'm going to go ahead and just change that to a minus 23320. The Kelvin have canceled, so I'm left with joules per mole. And notice the fact here that my delta G naught was 33 kilojoules per mole, meaning I'm going to have to, again, convert one of these guys. Always pay attention to units in this chapter. So I take my 23320 and divide it by 1,000 to convert to kilojoules. Right? So now I have 33.0 kilojoules per mole minus 23.3 kilojoules per mole. And I should get a final answer. Delta G is equal to 9.7 kilojoules per mole. That's a positive value, which tells me that that is a non-spontaneous process.